Good morning. We have a couple chapters left, chapter 30, chapter 31, still looking at electric and magnetic forces and fields and looking at circuits. And so chapter 30, well, let's get started. So let's see what we've got here. Now, chapter 30, kind of like these previous chapters, what are the names? The names here we have for the title of the chapter: inductance, electromagnetic oscillations, and AC circuits. It's mostly circuit stuff that we're going to be looking at in the chapter. So let's go ahead and get started. Now, we talked about transformers in the last chapter, in chapter 29, and so we're going to start off this chapter looking at something called mutual inductance and self-inductance, and we'll see that that's related to what's going on inside transformers in a little more detail. We'll look at energy storage, and then we're going to be looking at a bunch of circuitry stuff. Okay, so what we have is this. So what we saw with transformers is that we had a set of loops of wire, and then we had another set of loops of wire, and they were placed close to each other. Now, it doesn't have to be loops to have the effect that we're showing here, but the loops, what they allow us to do is create a more concentrated effect. And the idea with these loops is that the loops will generate a magnetic field. Loops, the first set of loops will generate a magnetic field, and the second set of loops will feel the effects if that magnetic field is varying, and vice versa. And so the second set of loops, if there's some kind of a variation taking place there in terms of the current, we'll end up with an induced current in the other set of coils. Now, in terms of Faraday's law, this is spoken of in terms of magnetic fields and changing flux. But what this is all a result of are acceleration fields. So at the end of the last chapter, at the end of chapter 29, we looked at what are called acceleration fields and showed that if we have current increasing in some direction in a wire, so the current is there, but the current also is increasing, that means that the charges are accelerating. And the result of accelerating charges is to produce what we call acceleration fields, and that is electric fields that are going in the opposite direction. So all I have to do to create this effect, I can put two wires next to each other, whether they're coils of wire or not, just two lines of wire. If I begin accelerating charges in one, that will create a force in the other one, pushing charges in the opposite direction. So if I accelerate charges in one direction, I will induce a current in nearby wires in the opposite direction, and that's because of this acceleration electric field effect that's going on. And so in the coils, what we're doing is we're concentrating that. What I've got is I got a bunch of loops here. If the current is varying, saying that if the charges in there are accelerating, these accelerating charges will create electric fields that actually set current into motion in the other loops. And that's referred to as mutual inductance. Now there's actually a unit for this. They're called henries, and the official formulas look like this. Now we're not going to do that much with mutual inductance. This is mostly conceptual, just to understand what's going on. But what we say is that the EMF set up in one set of wires is a result of the charges accelerating in another set of wires, and that factor, the mutual inductance, depends on how many loops we've got, how close they're placed together. So let's take a look and see. So here is two sets of loops. What I've got is I've got one of our solenoids that we've been talking about. We're going to send current through the solenoid. The solenoids have a cross-sectional area to them. And then what we're going to do is we're going to wrap the solenoid with another set of loops. Just a few loops in this case. And what we can show is that there will be a mutual induction that takes place And what we can say is that the EMF that gets set up here using Faraday's law is going to be equal to minus n, minus the number of loops times the change in the time derivative of the flux. So if I have a flux passing through here that is magnetic field due to the first set of loops, here is the magnetic field due to that first set of loops times the area. Now the flux that's being generated inside of the magnetic flux then can be related to, or the change in flux, the time derivative of the flux is proportional to the time derivative of the current. And that says that we can define then mutual inductance times di dt is going to be equal to N2 times the flux. Okay, so this is the equation we're working from right here. Mutual inductance times the time derivative of current 1 is equal to the number of loops in loops 2 times the time derivative of the flux. And so the flux that we have here is proportional to how many loops we've got, and then the EMF that's generated is proportional to how many loops there are in the second loop. What this all comes down to is that there's a mutual induction effect that depends on how many loops are in the first coil, how many loops are in the second coil. More loops means greater mutual induction. Depends on the cross-sectional area, and then it depends on the length. So it's kind of how compactified, how concentrated we have this effect, how close the loops are placed to each other. Now there's a more important effect for us. We're going to be spending actually more time looking at a process called self-inductance. So self-inductance starts from the very same set of formulas, except the difference this time with the self-inductance is this. So this is the very same diagram. You know, the loops, the original set of loops that we come up with, they're not just going to have an effect on neighboring loops, but they're going to have effect on each other. So this is referred to as self-inductance. If I just have one set of loops of wire, we can define what's called a self-inductance, and for that we use the symbol L. So the self-inductance times the time derivative of the current is equal to the number of loops times the time derivative of the flux. That's what Faraday's law tells us. Faraday's law is really handy here because it allows us to go in and work in terms of the magnetic flux, which is relatively easy to work with. Calculating the acceleration fields, the electric acceleration fields, can be complicated. There are going to be some situations where we want to go and you work from Faraday's law, and other examples where we want to directly calculate the acceleration electric fields. But for right now, here is the inductor. This is actually a device that we're going to start putting into circuits. Let's see, what have we looked at in circuits so far? Well, we've got batteries. We have power sources of different types. And then as far as devices, we have resistors and we have capacitors. So we're going to add one more to that list, and that is what we call an inductor. And an inductor is a fairly simple device. A solenoid, solenoids we've looked at before for generating magnetic fields, solenoids make really good inductors. Because what a solenoid does is it takes a bunch of current and it runs a bunch of current by other current. And so all these different charges are moving past each other. And what happens is if the current begins to vary, we'll end up with a voltage, an EMF generated within that inductor. So we've run through the very same set of calculations. What we end up with is this. There's a self-inductance formula, and that's the one that we're going to work from the most often, and that's what's taking place in a device called the inductor. And then there's what's called a mutual inductor effect, and that's between two different sets of coils, And this is what we looked at when we were looking at transformers. Transformers, we were interested in two distinct sets of coils and how energy could get, or energy and power could get transferred from one side to the other. For the self-inductance, it depends on the number of loops times the number of loops. It takes n loops to create the acceleration E field effect. So n loops create the effect and n loops feel the effect. So every loop feels the effect of every other loop. Okay? Every loop creates an effect, all of the loops experience that effect. Now, mutual inductance, it's a factor of n1 times n2. Otherwise, it's basically the same formula if we're working from the same geometry. So in this case, we've got n loops generating the effect and n2 loops feeling the effect, and vice versa. So self-inductance works something like this. The inductor, the symbol for an inductor, is this funny symbol like this. So we had, what was it? The capacitors were the plates, the resistors were the little zigzags, and now we have an inductor, and the symbol for the inductor in a circuit looks like this. And what happens is, if we have a current going through an inductor, and the current begins to increase, if we have a di dt, then the electric fields that are set up within an inductor, they push on everybody else and say, no, wait a minute, let's slow down, let's not raise the current too fast, let's not get carried away with this. And so inductors actually moderate changes of current. It's difficult to change the current rapidly if you have an inductor in place, because if the current begins to increase, the inductor pushes against that. If the current begins to drop off, the inductor creates an EMF that helps prevent that also. So the inductors kind of like things the way they are. They're a little reactionary. If they see things changing, they work to moderate those changes so they don't happen too rapidly. And so what we're doing here is we're saying if the current is increasing, then what's going to happen is we'll have this voltage drop across the inductor. So these EMFs that are being generated create effectively a voltage drop. And so we can organize them the same way we've organized resistors and capacitors, and we can add inductors to the list and say inductors create a voltage drop inside a circuit. So we've got the possibility of currents increasing or decreasing as we go through an inductor. Okay, and again, here is kind of the idea. We looked at some of this in chapter 29. Here is the inductor. And in the inductor, let's say that we have current going in this direction, and that we also have the current rising. So that means that we have an acceleration of the charges. We have both a velocity and an acceleration of the charge density. And if the velocity and the acceleration are in the same direction, then the current is increasing. All right. The other possibility is that we have a current going in one direction, but it's dropping off, and that would say that the di dt is negative, or in the opposite direction. And that would be like velocity one direction and the acceleration opposite. Now, the way these acceleration fields work, these electric acceleration fields, and again, if you need to go back and review the end of chapter 29, the notes there, take a look at those notes, or go back and watch the last part of the chapter 29 lecture. But we're going to end up with electric field, acceleration fields that are opposite to whatever direction the acceleration is in. Now, in this example, the acceleration was in the forward direction, which means the acceleration fields are opposite, which means they're going to work against increases in the current. Now, if the current's dropping off, then the electric fields that get generated, again, they're going to oppose the direction of acceleration. And that means that the electric fields that are generated are in this direction, and that helps to boost the current. So inductors moderate variations that are taking place in the current. the electrons are either accelerating or decelerating. They're speeding up or slowing down. And the electric field will push backwards or forwards on neighboring electrons. Electrons that are slowing down push forward on neighboring electrons. Electrons that are speeding up push backwards on neighboring electrons. And that's what modifies the changes in the current. Now there's a bunch of stuff with the transformers here. I'm not going to spend a lot of time here. I did outline all this, so if you're interested, transformers depend both on the self and mutual induction effect. We talked about transformers last chapter. So in a transformer, it's not quite as simple as saying the energy transfers from here to here, because there's self-inductance on this side, there is self-inductance on the secondary, and then there's mutual inductance between the primary and the secondary, and there's a mutual inductance effect between the secondary and the primary. To get the full effect, we go through, start out by, again, we did a derivation of this in chapter 29. We're coming back and doing this a little more thoroughly now. In this example, we're including the self-inductance effects as well as the mutual inductance effects. And it says that the voltage in the primary is going to depend on how the current there is changing, multiplied by a self-inductance or an inductance. And then there's a mutual inductance effect with the other side. So anyway, if you're interested in seeing all the details, it's a nice set of symmetric equations. But we're going to move on. We're not going to spend quite that much time. If you remember, back in chapter 24, I think, when we were studying capacitors, we showed that there was a formula that told us how we could calculate the energy storage in a capacitor based on the electric field. Not on the voltage and the charge, but on the electric field. And so it turns out that there's a completely analogous energy density associated with magnetic fields. And so we can work from basically the same formula. Now, the textbook is working in terms of mu naughts and epsilon naughts for these energy densities. But what I've done, and what we've done in class here, is we've stayed with the electric magnetic force constant, the very same little k, the 8.99 10 to the 9th newtons meters squared per coulomb squared. And by doing that, when we get to energy densities, this is some number of joules per cubic meter, the formulas are identical. So it's 1 over 8 pi k times the electric field squared. And the energy density formula for magnetic fields is 1 over 8 pi k times the magnetic field squared. Now, if you remember, historically, for historical reasons, magnetic fields are measured in different units compared with the electric fields. But if we want to put them on equal footing and compare them in the same set of units, all we have to do is add a factor of c. And so when I put the CB in here and square it, the energy density formulas are identical. So let's take a look at a couple of examples. Let's say we have a region where the electric field is 400 newtons per coulomb. The energy density would be 1 over 8 pi k E squared. Plug all the numbers in, check the units. The energy density within this electric field would work out to be 707 nanojoules per cubic meter. So again, it's an energy density. It's not just an energy. The units are going to be in joules per cubic meter. If we have a magnetic field where CB has the very same value, now since CB has the same value of 400 newtons per coulomb, B by itself, which is in Tesla, works out to be 1.33 mic. So that's just an aside here, that if we put the magnetic field back in Tesla, which are official standard units for magnetic fields, it would be this number. But the CB, if the CB matches the E, then we have the same energy density. Okay, the same amount of energy stored in that magnetic field as in a comparable electric field. Okay, you guys ready for a bunch of circuits? We have a bunch of circuits, kind of through the rest of the chapter, I guess. So let's start. First of all, we're going to start off with a DC circuit, well, kind of a DC circuit. What we're going to do is we're going to work from a circuit that's running off a battery with fixed voltages. And what these are LR circuits. Now, R stands for resistor, and L, I think we mentioned this, inductance, the symbol we use for inductors, for the inductance of an inductor, is L. It wasn't my idea, but that is what we use. So I is used for current. Well, that doesn't make sense either. Anyway, so we're going to use L, capital L. So this is what inductors look like in our diagrams. And L represents how much inductance, and inductance is measured in henries, just the same way that resistance is measured in ohms. All right. Now what we find is that when we switch, when we move the switch so that the battery is included here, we start at no current at all, and then the current is going to increase. So the current's going to rise. Now, before, when we did these circuits, earlier in the course, we said that immediately the current goes from 0 to some finite value. Well, that's not quite true. Circuits have this effect of inductance in them, and so I mean, every circuit has a little bit of inductance, I guess, but this circuit actually has a dedicated inductor. And so what's going to happen is the current is going to rise and asymptotically approach some final value. Hey, we've seen this before, right? This is what we saw with charging a capacitor. So the formulas that we developed for charging a capacitor work the very same way when we are looking at an LR circuit and we're looking at current. So there are going to be time constants. As the time constants here are given at the bottom there, the tau, the time constant, is given by L divided by R. And once one time constant has gone by, the current will have risen to 63% of its asymptotic value. So here's what the differential equation looks like. You don't have to solve that. This is what the solution looks like. So again, it's our friend, 1 minus e to the minus t over a time constant. The only difference here is that the time constant now is L over R. It's determined by how much inductance and how much resistance we have in the circuit. So there's a lot of stuff in Chapter 30. So Chapter 30 really has a lot of stuff. And so what I'm going to try and do here, and the examples that I've chosen to include in lecture, really try to focus on the items that are going to be most important for us. And so we're not going to worry about all of these details in a lot of these examples. We're going to try and focus on what are kind of the most important set of concepts, and get some practice looking at examples with those. So here's an example in any case. There's my switch. I do like that they use the symbol S for switch. That's interesting. So here's my battery. It's a 12-volt battery, and the resistance is 30 ohms. Now the inductance is 220 millihenries. And so we're seeing some numbers show up here with the inductance. And it just looks like back when we were solving for capacitors in RC circuits. So what's going to happen is that the current is going to rise, it's going to have some asymptotic value, and the where is that? Here we go. The asymptotic value, once we get to infinity, the current will have risen to V naught over R, and with the numbers we've been given, it's going to eventually reach 400 milliamps. And it's going to reach it by this 1 minus e to the minus t over tau function. That's what the graph looks like still. And then what this is asking about is what's the power? So at a particular instant. So let me go back and reread the formula a little more carefully, I guess. What it's saying here is we're going to start off at t equals 0, close that switch. The battery is connected in series with the inductor and a resistor. What will the current be initially? Well, because of the presence of the inductor, initially the current is going to be 0, right? What we find with an inductor is inductors go, wait a minute, hold on, we're not going to do this in a big rush. We're going to let the current gradually increase, and eventually you're going to get to that asymptotic value, or closer and closer to the asymptotic value. So that's what the inductors are doing in the circuit. So the current at t equals 0 is going to be 0. What's the time constant determined by? And the time will get stretched out based on how much inductance there is. More inductance means that the current in the circuit is going to rise more gradually. And then it's actually divided through by the resistance. So again, what the resistance is doing is it's setting up what the asymptotic value will be. If I have a lot of resistance, the asymptotic value will be much lower, and it's not going to take as long to get there. Okay, so the current eventually would be expected to reach the value V0 over R, which looks like, you know, 0.4 volts or 400 millivolts. All right, and so that's what determines the time constant. What's the maximum current? That's V0 over R. How long will it take the current to reach 1/2 of its final value when the current has reached its 1/2 of its final value? What is the rate of energy being provided by the battery, and where is that energy going? So these are energy rates, and energy rates are power. So let's take a look and see what we've got here. First of all, here we go. This is the 50% level is here. So at 50%, 50% is less than 63%. So it means less than one time constant has gone by. Now, to make this 1/2, I actually want to take the e to the minus t over tau and set that equal to 1/2. So I can do a natural logarithm of both sides, multiply through by the time constant. And it says that the time we're looking for is tau times the ln of 2, and that is 5.08 milliseconds. Now, what was the time constant? Oh, here it is. Good. So one time constant for this circuit, which is given by L over R, is 7.33 milliseconds. And we will reach 1/2 of the final current after 5.08 milliseconds. All right. So the current at that point will be 1/2 of its final value. And so what we can do then is take, we can figure out how much voltage there will be. So when the current is at 1/2 of its value, that says that the voltage across the resistor will be 6 volts, and the voltage across the inductor will be 6 volts. So that says when the current is at 1/2 of its value, the voltages are evenly divided between voltage drops in the inductor and voltage drops in the resistor. Okay, as far as power, I can take the voltage and multiply by the current at that instant. Now I can do that for the inductor, and I can do that for the inductor, and I can do that for the resistor. So VR times IR. Now I have those values, 6 volts times the 0.2 milliamps. That gives me 1.2 watts. If I do the same calculation with the inductor, I'm going to get 1.2 watts. Now what we could do, just to double check, is I could take R times I squared for the resistor, and for the inductor, I could do L times di dt. And when I do the L di dt to calculate the voltage, and then multiply that by the current, again, what I find is I'm getting 1.20 watts. Now, I don't see that we calculated the power coming out of the battery, but that should be easy enough to do. The battery power at any given instant is the voltage of the battery, 12 volts, times whatever the current is. And so if the current is at 200 milliamps, 0.2 amps, times 12 volts, that's going to give us 2.4 watts. So the battery is providing energy at a rate of 2.40 watts. Half the energy is going into the resistor and being thermalized. Half the energy is going into the inductor. Now, what is an inductor doing with energy? And inductors store energy in their magnetic fields. So just the same way that capacitors store energy, inductors also are energy storing devices. So inductors can take energy in and store that as magnetic field energy, and then they can release that energy back out to the circuit. So when I look at a circuit, the resistors are thermalizing energy. So resistors indicate to us a place in the circuit where electrical energy is being lost or being converted into thermal energy. But the capacitors and the inductors both are going to be storing energy and then releasing it back into the circuit at a different time. All right, so now we said we have a lot of circuits to look at. We looked at some LR circuits. We went through some of the formulas and looked at those. Now let's look at, let's see, we've looked at RC circuits. That was resistors and capacitors. We looked at LR circuits. Those were inductors and resistors. The only other two-device combination I can think of are L's and C's. So let's do that. So what we're going to do is we're going to do an LC circuit. Now, since a resistor is not present, there is no way to get rid of the energy. And so we don't have to put a battery in this circuit. And it would be simpler to leave the battery out, and as an initial energy source, let's just say that the capacitor starts out as being charged. So again, instead of having a battery as a steady energy source that keeps providing energy to our circuit, we're not going to use that. We're going to have a capacitor that stores energy initially, and then an inductor, and then we'll have our switch, and we're going to close the switch. Now, if I close that switch, the charges on the plates of the capacitor, these positive charges will head out and create a current, and of course that current will be simultaneously set up throughout the entire circuit. And so as soon as we close the switch, I'm going to have electrons moving in this direction. Electrons are coming off this plate, electrons are jumping onto this plate, and then everywhere through the circuit, the electrons now are in motion. So as soon as we close that switch, the capacitor begins to discharge. But the capacitor is discharging through an inductor. And you know what inductors say about rapidly changing currents? Say, no, let's hold off, let's not let the current go increase too rapidly. So how are they going to work this out? So the capacitor is ready to discharge into the circuit, and the inductor is preventing the current from rising too rapidly. Well, here's where you go back to the mathematics, and you say that what we're going to end up with here is a differential equation representing how these circuits are working, and the differential equation that we end up with in describing this tells us that the charge actually is going to be oscillating. So if we go back, so I'm not going to worry so much about the details of those equations as much as coming back to this picture and saying what's going to happen is this. The electrons are going to move through the circuit, the capacitor is going to discharge, But what's going to happen is the capacitor is going to overshoot. It's going to discharge all the way, but when it's discharging, it's going to overshoot, and because of the presence of the inductor. So it's going to take some time to get all of that current moving through the inductor, but once the current is built up, the inductor wants to keep the current going. And so the effective inductance here is once the capacitor has fully discharged, the inductor makes sure that the current continues in the same direction, and that's going to make the capacitor charge in the opposite orientation. So the capacitor will end up recharging, but this time it will recharge with the pluses and the minuses reversed. So the pluses and minuses are going to reverse on this. And what we end up with is that the charge on the capacitor as a function of time, and I'm really at this point focusing mostly on this solution right here, what we find is that the charge as a function of time follows a cosine function. And the reason it's a cosine is because at t equals 0, the capacitor was fully charged. I'm actually not going to worry about this phase angle. You may remember phase angles back from chapter 14 when we're looking at oscillations. If we start with the capacitor fully charged, we can write this just as a cosine function. Now, what is going to be the frequency at which this circuit oscillates? And the frequency at which it oscillates is given by 1 over LC square root. So that's the formula we're going to end up with. And then if the charge on the capacitor is varying like a cosine function, what does that say about the current? And the current will be varying like a negative sine function. Now, we ran into this once before. When capacitors are discharging, our textbook likes to put a minus sign into this definition. And I think by doing that, you kind of hide what's going on. And what's going on here is that when the capacitor is charging, we think of the current coming in as being positive, but when it discharges, I want something to tell me the current's going in the opposite direction. So I actually kind of like having the minus sign left off here, and instead have the minus sign show up over here and say that because the capacitor starts out fully charged, when we first throw the switch, the current will be going in the opposite direction to the direction that was used to charge it. Okay, now they're going to use sine functions, so we can deal with that. So here's what the charge in the capacitor looks like. Now what you can see is that it's just cycling. That is, 1/2 of a cycle completely reverses the charge on the capacitor. And then a full cycle would be going from the capacitor fully charged with one particular charge orientation. It reversed at half period, and then it reverses again, and it's back to the same plate is now negatively charged, and the same plate is positively charged as when we started out. All right. And the current during that time, notice that the current is out of sync with the charge. When the capacitor is fully charged, well, that's the instant at which the current has momentarily stopped. And vice versa. When the capacitor is going right through 0 charge, it's completely discharged, that's actually when the current is moving its fastest. Okay, so the current is the largest when the capacitor is going through its instant of being fully discharged. Now, those are the formulas that are predicted. We can go into the lab, we can measure the currents, we can measure the charges, and it turns out that this is an accurate set of formulas telling us how this will work. Now, what about energy? And so we have a couple formulas for energies of, first of all, the capacitor. One of the formulas that we came up with for the energy storage in a capacitor was 1/2 Q squared divided by C, so we'll write that down. And then what we can also do is we can introduce this new formula This is the energy stored in the magnetic field of an inductor. So this is the energy stored in the electric field of the capacitor, energy stored in the magnetic field of the inductor. And what we can show is that the charge is varying like a cosine function. So Q squared becomes cosine squared. And so the red line is showing how much energy, as a function of time, how much energy is stored in the capacitor. And as we mentioned, or we remarked, we're going to start with all the energy in the capacitor. So the red line starts right up at that total energy dashed line. That dashed line is the total energy in the circuit. And then when we close the switch, energy from the capacitor leaves and goes into the inductor. So as the capacitor discharges, a current is increasing, and as the current increases, that's more and more energy in the inductor. Remember, the inductor is storing energy in its magnetic field, and the magnetic field is proportional to the amount of current going through the inductor. So when we add up both of these, the energy storage in the capacitor behaves like cosine squared. Again, I would just set these phase angles to 0. Those are for instances where we don't start with all the energy in the capacitor, and we're not going to look at anything like that. This is enough for us to see the effect that's going on. And so the two energies add together at every instant. I can add the sine theta, or the sine squared omega t, and the cosine squared omega t, and they add up to be 1. Okay, so basically we're accounting for all the energy. Now, this isn't quite true. And so what we've done is we've idealized this circuit by saying there's absolutely no resistance, and that's not likely. There's going to be some resistance somewhere. So we're going to get some thermal energy generated typically. A second item that we have to keep track of here, we'll see in the next chapter, is anytime we have charges that are accelerating, those accelerating charges are going to radiate energy. Their electric and magnetic fields are actually going to carry energy away from the circuit. This is going to turn into a little radio broadcaster, or a little cell phone broadcaster, where energy is being transmitted away from the circuit. So those are a couple things that we've ignored. When we ignore those, in the simplest of cases, then we end up with these solutions where it's just a pure cosine function, a pure sine function for the current, and that the energy never depletes. So in the ideal case that we're imagining, this oscillates forever, right? There are no energy losses due to radiating photons, radiating electric and magnetic fields, and there's absolutely no resistance in the circuit, so no thermal energy is generated. Both of those are, you can imagine, a little idealized. The one that I want, for you guys to keep track of, certainly the thermal energy effect. You guys are probably experienced enough in physics to go, yeah, there's always going to be some thermal energy generated. But this radiative thing, we'll see that in the next chapter in some detail. That's going to be really interesting for us too. So just to keep in mind, whenever we have these charges accelerating, we're going to be radiating photons. We're going to be radiating in some part of the electromagnetic spectrum, maybe in the radio part of the spectrum for circuits, or the microwave part of the spectrum when this is happening. All right, so here's an example. We're going to do an LC circuit. Let's start out with a capacitor fully charged. There's an inductor that's 75 millihenries. Let's go through and solve for everything. Here we go. So there's an LC circuit, and this is really important. We're going to be looking at a number of circuits, and I'm going to suggest, sometimes students go, what's the best way to organize all this material? And I would say the best way to start with is to say, when you look at a circuit, what power supply are you working from? So we have worked from batteries, from DC power supplies, if we have a resistor and a capacitor, or if we have a resistor and an inductor. So for RC circuits and RL circuits, also known as LR circuits, we have a battery in place. Now we've moved on to a couple of circuits. We're going to look at this one and one more where there's no power supply at all. And the idea is that the energy we start with is going to come from a charged capacitor. Okay? So again, I think always ask yourself the question, what's my power supply? And for this circuit, there is no power supply in terms of a battery. Instead, we're going to start work from the energy in the capacitor. So they've given us values. The capacitor is at 1200 picofarads. The inductor is 75 millihenries. And that says that, all right, what was the volt? I want to double check and see. They must have given us this 500 volt number. Let me check and see. I didn't get that written down. I apologize. That should be in my given. Yes, it's right there. So I missed this. The capacitor was charged using a DC power supply. So initially we took the capacitor, we attached it to a 500 volt source, charged those plates to 500 volts, then we disconnected the capacitor, brought it over, and put it in this circuit instead. So now it's in a new circuit. The switch has not been closed yet, but there's an inductor. And so this is given. I needed to get this up somewhere. I don't see that I wrote it down. I apologize for that. Anyway, using the 500 volt value they gave us, multiplying by the capacitor, that tells us the amount of charge on each of the plates of the capacitor initially will be the 600 natacoulombs. So I hope this is familiar, right? This is something we saw back in chapter 24. And I know when you get into these circuits, it's like when you see something familiar from previous chapters, it's like, yes, that really helps. That kind of anchors these new ideas into something I'm already familiar with. So anyway, that's how much charge, that's the voltage, that's the capacitance of the capacitor. Now, once the oscillations begin, what we've shown is that the maximum current, well, let's go over, we've got it outlined here too. So if the charge is going to be varying like a cosine, the current is going to be the time derivative of the charge. So anytime I can get a function telling me what the charge looks like as a function of time, I can take a time derivative of this, and that will give me the current. So I is going to be equal to dq dt for these circuits. Now I could take one more step back and say it's an LC circuit. There are no voltage boosts. There are no batteries. There are no generators. So it's really up to the capacitor and inductor. And in our equations, what we've always done is listed the capacitors and the inductors as voltage drops, not voltage boosts. And so the voltage across an inductor is given by inductance di dt. So if you go back to the beginning of the chapter here, you'll see that formula being used to represent the EMF, the back EMF. And what that produces for us in a circuit is a voltage drop. So this is the voltage drop for the inductor, this is the voltage drop for the capacitor. Now I add those together. Now you might be thinking, well, wait a minute, I can't have just voltage drops. And so what happens is one of these voltage drops at any given time actually has a negative value to it. So the inductor and the capacitor can serve either as a voltage drop or as a voltage drop in the opposite orientation, let's say. And so they can keep the circuit going. Let's see mathematically how that works. So I'm going to take 0. There are no dedicated voltage sources here. Set them equal to the two voltage drops. It's up to you guys to get this circuit to work. I plug that in. Now the current in this circuit is given by dq dt, And di dt requires a second derivative. So di dt becomes the second derivative of charge with respect to time. We're just going through this for purposes of showing mathematically how this comes about. You guys are not responsible for solving these differential equations. But I'm hoping, at least for a good number of you, that this is something that's somewhat familiar and actually is making some sense. So what we do is we come back up to this circuit, to this formula, and say the second derivative then can be set equal to, solving for this, 1 over LC QT. Now there was an earlier slide that had this formula listed. When we solve that equation, the solutions are sines and cosines. Because if I take the second derivative of this function, I get the same function back again with a minus sign with some constants. Now what that enables us to do is I can write down what the charge is as a function of time. I can take a derivative, write down what the current is as a function of time. I can write down what the maximum current will be in terms of the beginning charge that we start with. And then finally, the frequency of the oscillations squared is equal to 1 over LC. So this is where the frequency is coming from. And let's plug those numbers in. So the frequency that we're going to get, we take a square root, that's a pretty high frequency. Oh my gosh, we must have really low values of capacitance. That we do. So it's a pretty low value for capacitance, a pretty low value for inductance. Let me just do a quick check here. Yeah, I think that actually makes sense. So the radiance frequency is about 105 radians per second. So if I put that in terms of hertz, this circuit oscillates back and forth. The current's oscillating back and forth 16,800 times a second, okay, as a frequency. All right, and when it radiates, it's going to radiate photons with that frequency. So kind of, you know, something to think in looking ahead towards radiation of electromagnetic fields. All right, did we get everything solved for? We got the maximum charge. We took the omega value multiplied by Q naught, which is what the formulas here were telling me to do. It says the maximum currents we're going to reach are 63.2 milliamps, and that the energy in the circuit we can get by going back and looking at the original capacitor being stored with Q naught and to a voltage of V naught. So the circuit has 150 microjoules of energy. And since we're idealizing this circuit, imagining there are no energy losses anywhere, that's a fixed amount of energy in the circuit forever, because it's going to oscillate forever, because we've ignored thermal energy generation and we've ignored radiation of photons. Okay, radiation of basically light of different parts of the spectrum. Okay, so that was a good circuit to look at with the inductors and the capacitors. Now let's get a circuit that's a little more realistic, and we can do that by putting a little bit of resistance into our circuit. And I'm thinking it's probably time for a break. So maybe this is a good place to take a break. I'm going to say yes, it is. So let's do that. Let's take a break for 10 minutes or so, and then we'll come back and look at the rest of chapter 30. If you guys have any questions, stop by.